So Matt Mukherjee and David Naylor are two students at Carnegie Mellon who've been working very, very hard in the last week plus to put the demo together with Dan Barret, also from Carnegie Mellon. We also had a lot of help from, and have incorporated some of the contributions from Cody Duchef from Boston University, Michel Machado from Boston University, and Robert Grandel from University of Wisconsin. So a lot of people contributed to the demo. So the procedure is that I'll give a very short overview of XIA, and then I'll basically hand it over to Matt and David to talk about to run the demo. So XIA is one of the future Internet architecture projects that are funded by the National Science Foundation, and we're very grateful to NSF, obviously, for their support. So a little bit of motivation. So one of the things I always like to do in a future Internet architecture talk is to give credit to the current Internet. Obviously, you can't argue with its success, and I think one of the reasons for the success is really kind of the fundamental architecture, which is based on an hourglass model, as many of you know. But we've also observing that the narrow waist of the Internet today is introducing some challenges that are very difficult to tackle. And, so these include things like security, which I think we're all aware of. It's also hard to evolve the narrow waist. One example of that is that the Internet is a host-based communication, provides host-based communication, even though virtually no applications care about hosts. They care about services and content. And then finally, the contract between the network and the endpoints, which is really what the IP architecture does, is actually very limited, and that's also becoming an issue. So I'll present a couple of ideas that we have and that we're exploring in XIA to fundamentally address these challenges. So there's the first of the three ideas is that instead of being able to send packets to just hosts, which is the model in the current Internet, you can send packets to different types of entities, okay? And I'll call these things principals. So what's important here is that even though I'm going to use endpoints to identify the different types of principals, what is fundamentally different between the principal types is the fact that they have different forwarding semantics inside the network. So this is really about how the network handles these destinations. So quickly to go through them, we still have host identifiers similar to the current Internet. So that really means that you're sending a packet to a particular piece of hardware, a particular network attachment points. We have service identifiers as well, and the difference with hosts is that services can be replicated. So you can have multiple instances of a particular service, and we're giving the network the flexibility of picking the one that's the best one in terms of being the closest or whatever. And then finally, we also have content principal type, which differs from the above in the sense that content can be opportunistically cached and potentially very, very massively cached. And so the network may have many, many choices for delivering the content that is requested. On top of that, we have autonomous domains as well, which we are using for things like scoping and hierarchy, as I will show later. What's important here is that we want this set of principles to be able to evolve over time, because 10 years from now, nobody may care about services and hosts anymore. We may have come up with something better, okay? And I don't know what it is, and it doesn't really matter because the architecture will be able to adapt. So I'll give you a very quick example of how this works. Suppose we want to retrieve a web page. The way this could be done is by saying, look, maybe I'll pick CNN. The CNN service may be in fact replicated. And so the network may have a bunch of choices about which service instance will deliver the content. One of these services will return a front page, and it will use a blue arrow, which basically responds to host-to-host communication to return that front page. It has a bunch of embedded objects which can correspond to services or content or other things. And so now the host can basically use services or content identifiers to retrieve the remaining pieces of the front page of the service. And different components in the network can basically deliver them depending on who happens to be in the best position to do that. And the network plays a key role in making that happen. So content in this case can be opportunistically cached as is suggested here. And so hopefully this quick animation will give you the main idea. The second piece of the puzzle is that we want to support evolvability. And as I mentioned earlier, this involves basically being able to evolve the set of principal types. So the key challenge here is that whenever you introduce a change, the question is who is going to be modified first, applications or endpoints? And this is a traditional chicken and egg problem in the sense that there's not much of an incentive for one to change if the other one hasn't changed yet. So the particular proposal that we have is based on a concept called fallbacks. So in this particular case, let's imagine that we have a host-based internet and we want to add content identifiers represented by CIDs. An application can send a packet like that, but it's likely to get in trouble because there will be routers in the internet that don't support CIDs. So they're going to drop the packet and the application is going to fail and whoever wrote the code is going to be in trouble. Okay? So what we propose instead in XIA is that addresses can in fact have multiple identifiers as part of the address. In this particular case, besides the CID as a destination address, there is also an old-fashioned address consisting of an autonomous domain identifier and a host identifier, which basically identify the host using a well-established addressing format. Okay? And so any router in the internet can basically fall back to that particular address if it doesn't recognize the first one, the CID type. So it's a very simple idea. So specifically in XIA, we implement this using DAG-based addresses, which is a little bit of a stretch, but is actually quite intuitive. Here I have a destination address that consists of just a CID. Suppose I'm a router and I don't know what that is. I'm 10 years old and I have no clue what this is. So what I end up doing is, there's a second part of the address which corresponds to the second part I had in red on the previous slide, which effectively corresponds to an autonomous domain identifier and a host identifier shown at the bottom here, and that's the fallback part. So edges here are basically being followed by routers as they forward the packet, and we have solid edges, which are the primary edge, and fallback edges. Any router in the internet can basically, if it doesn't recognize the priority edge, it can fall back on the fallback edge and deliver the packet using those well-established identifier types. That's the key point, okay? And you will see this later in the demo as we show that. The final part of XIA is basically intrinsic security, and this is that each principal type or communication based on each principal type has some intrinsic security properties associated with it that allow you to verify certain properties of that communication operation. Okay? And so I'm not going to spend too much time on this because this is actually largely relying on earlier work, such as the AIP, the Accountable Internet Protocol. The thing you will see in the demo is actually an example of intrinsic security for content, where the identifiers associated with content are hashes of the content themselves, so the destination can verify correctness. And then finally, I want to emphasize the kind of how these three pieces fit together. So I've explained three ideas that are being explored within the context of XIA. Basically, as I hope I've been able to briefly explore, each of these three ideas has value in their own right. Okay, so each one of them you could actually implement independently of the other, and you will get some benefit from this. On top of that, by combining these three ideas, we get additional value. So an example that I will pick out is that by having flexible addressing, by having multiple principal types, and we combine this with flexible addressing based on DAGs, we can actually evolve the set of principal types. If we had just flexible addressing types, that would still be useful, but we couldn't evolve it. So basically, the flexible addressing adds evolvability. Okay? And so we are now in the process of basically moving these ideas further and evaluating them. And so now I'll hand it over to Matt and David, who will actually give you the demo.
All right, thanks, Peter. So as Peter said, I'm David, and this is Matt. We're both PhD students at Carnegie Mellon working on XIA, and we're really excited to get to show you XIA running on GENI this morning. In particular, there are four things we want to show you today. First, we want to show you one example of evolvability in XIA. Secondly, we're going to show you an example of intrinsic security in XIA. Third, we're going to show you a way we can deploy XIA on top of IP networks. And fourth, just for fun, we're going to show you our Wireshark plugin. Before we dive into the demo, I just want to briefly describe our topology. We sat down and thought hard about the most interesting topology we could think of, and a straight line seemed to be the answer. So we have 4 nodes running on GENI. 2 of them on the left here are the nodes in Japan that Mark talked about. And then on the far right, we have a host at Carnegie Mellon, which is going to be talking to our GENI topology. And really quickly, I just want to extend a big thank you to Mark Berman, Rob Ritchie, Shu Yamamoto, and Aki Nakao for helping us get this set up. They were very instrumental. So for our demos today, we're going to be running a web server on a node in Tokyo. We're going to be running a web browser on the node at CMU. And I want to emphasize that these are native XIA applications. They're written in Python on top of our XIA socket API. And these applications do not understand IP. They speak only XIA. So let's dive into the first thing we want to show you, which is how XIA supports evolvability. So imagine our network, and the routers are fairly dumb. They only understand the host principal type and the domain principal type. So this network basically functions as an IP network would. You know, an IP address is essentially identifies a domain and a host, and that's what the host and domain principals do in XIA. But some clever application developers have developed a web browser and a web server that actually want to use a new principal type, the content principal type, to exchange web pages. And so we're going to show you that we can actually run our web server and our web browser with the content principal type, even though the routers do not understand what content identifiers are. And the way we're going to do that is with a DAG. So the web browser would like to send the following DAG into the network, just with the identifier of the piece of content it wants to retrieve. But if it does so, that first router there that only understands hosts is going to drop it. So we add fallbacks. When that router sees this DAG, it says, I don't know what a content identifier is, but I do know what domain and host identifiers are, and I can forward your packet. So we're going to transition to a web browser here, and give us one moment to restart the visualizer. It's been a little finicky. All right. So we're going to we've loaded actually a copy of the XIA homepage onto our XIA web server, and we're going to load it using the DAG we just showed you, and there it is. So we just loaded this using a content identifier with host and AD fallbacks over a network that only understands hosts and domains. And so let's load one more page just so you can see it again. And you'll notice on the visualizer we're seeing spikes of content going across, so we've got end-to-end connectivity using content identifiers, even though the routers don't understand them. So that's all well and good, but if application developers start using new new principal types, I mean, what's the benefit? If none of the routers support them, do we need to wait until all of the routers support a new principal type before we can actually see any benefit? Another way to say that is, what's the incentive for an application developer to start using new principal types? And what we're going to show you next is you can actually get immediate incremental benefits for upgrading even just one router in your network to understand a new principal type. And so what we're going to do is upgrade the router in Houston there to understand the content principal. So we're going to give it a content cache. As it sees content go by, it's going to cache it, and later when it sees requests for particular CIDs that it has in its cache, it will respond with those directly. So we're going to go back to our XIA page, and we're going to load up another page. We've upgraded the router in Houston to understand content. All right, so you see the spike of content traffic going all the way across from the web browser, the web server in Tokyo to our host at CMU. Now Matt's going to reload that page, and what you're going to see is you're only going to see traffic on the link between Houston and CMU, because Houston understands content and it has cached it. And so you just saw the purple line get big and fat, and now you see a second spike of content on the Houston CMU link, but not on the other links, because that router now understands the content principal and it can respond with the data from its cache. And so that, in a nutshell, is evolvability in XIA. And I would love to explain it more, but we need to move on to the other things. So we're going to now show you a simple example of how XIA's intrinsically secure identifiers can be put to use. So just a reminder of what Peter explained, intrinsically secure identifiers mean a different thing depending on the principal type. So a host ID is the hash of the host public key. A service ID is the hash of the service's certificate. And we're going to focus on content today. A content identifier for a chunk of content is the hash of the chunk of content itself. And so what this means is, in our example of a web browser fetching content, it will send a request into the network for a particular content identifier. It's going to get back a chunk of data, and it can verify that it received the correct data by hashing that data and comparing it to the identifier that it originally requested. And if there's a problem, it can alert the user or do whatever it needs to recover. So we are going to demonstrate this to you by making the router in Houston malicious. It is periodically going to respond to content requests with the wrong content, and you're going to see our browser will catch this. So let's go back to the XIA page, and we're going to load up another page. This one actually has some photos on it from our GEC demo, GEC 12 in Kansas City last year. And so you see we've got a couple pictures. There's Matt up on the top, and this is Dong Su, another PhD student on XIA. And all right, so we've loaded this page, but we're going to refresh. Aha, the router has responded with the wrong photo. And now give it just a moment. So this is running on the host at CMU. I should have mentioned we're using an HTTP proxy. And so things are a little slow, but a box is going to pop up any moment now that warns us that we've received the wrong content. Well, Houston, it appears we have a problem. This has worked every other time. Let's try refreshing it once more. So this time the router has responded with the correct content because we wanted to go back and forth so we could show you what it looks like in both scenarios. We'll refresh it one more time. We got the wrong content again. Actually, I see a TK error in the background, so I apologize. X forwarding has broken, but that TK error was TK trying to pop up the box. So the browser did catch the error, and if TK were cooperating, we would have seen that it alerted us to the bad content. So let's go back to the slides. And that is a very simple example of intrinsic security in XIA. All right, third, we want to show you how one might go about deploying XIA on top of an IP network. So at this point, I have a confession to make. I've been hiding something from you all morning. There is no link between Houston and CMU. In fact, there's just the IP internet. Actually, the IP internet too, but for the purposes of this demo, it's the same. Now, how have we been communicating with the web server, which is in our XIA network on GENI, if CMU and our XIA network are not connected directly? Well, we've actually introduced a new principal type, the IPv4 principal type. Now, an IPv4 ID, or a 4ID for short, is the IP address of an ingress router to a remote XIA cloud. So let's put the IP addresses up. So the router in Houston is actually a dual stack router. It speaks XIA and it speaks IP. Its IP facing port has this IP address. Our node at CMU has that IP address, and we're going to use these in 4IDs to achieve communication between these disjoint XIA clouds. So I told you that this was the DAG that the web browser was using to request content from the web server. In fact, this is the DAG we were using. We had an additional fallback that included the 4ID, which is the IPv4 address of the router in Houston. So when the XIA, when the web browser on our host goes to forward it, it says, I don't have entries for this domain, this host, or this CID, so I'm going to fall back and send this packet into the IP network. It'll travel through IP. It'll arrive at Houston. The router in Houston will see that this packet is addressed to me, pull out the XIA packet inside, and forward it into the XIA network running on GENI. Now, how do responses get back to us? Well, we do the same thing. We add a 4ID fallback to the source DAG with our own IP address. Now, I want to stress that this is not a statically configured tunnel. This is dynamic per-packet encapsulation. The only piece of information that the host at CMU needed to know was how to contact an XIA name server. The XIA name server responded with that DAG on the left, which included the 4ID that the web browser needed to reach this particular XIA network. We could run a different application on the host at CMU that wanted to talk to a different disjoint XIA network, and the name server could give us a DAG with a different 4ID in it to get those packets there. So that in a nutshell is how we can think about deploying XIA on top of IP. And finally, we just wanted to show off, we have a Wireshark plugin that's really great for debugging your XIA network. So we actually captured a packet trace of exchanges between our web server and our web proxy, and so Matt's just going to pull that up. All right, so this is, this is just a pretty standard-looking packet trace in Wireshark, but you see that it recognizes that the protocol is XIP. That's what we call our forwarding protocol. And we can open up the XIP section, and you'll see all of our header fields there, most notably source and destination DAGs, so we can expand those and see the DAGs in ASCII format. And this was very helpful in debugging our demos. So that is our Wireshark plugin. So those were the 4 things we wanted to go over with you today, but there is one more thing. Most of the stuff that you saw us do today, you too can do. We have a publicly available XIA prototype. You can download it as a tarball, you can check out our repository on GitHub, or you can download a VM that has our source and the environment already configured for you. On our wiki, we also, of course, have detailed instructions on how to get XIA up and running on GENI, so you can do this yourselves. And all of this and more is available at our homepage here. So that's what we have for you this morning. Thank you.
So that was a wonderful demo. Thanks, David. Thank you, Matt. Thanks, Peter. So we've just seen a really exciting bit of collaboration. We've seen XIA, which has been using some of the basic underpinnings of GENI to run a extended series of experiments over time. We've seen them extend this network out into a federated, non-GENI set of resources, the B nodes running in Tokyo. And I won't say it was easy, but it did work, and it took a finite amount of time. So this is a really neat thing to see.